Some of the people clicking on this video might fear they've just stumbled into the trap of clickbait, but don't worry, I've got the content to back the premise, because today we're looking at second order differential equations, and ultimately I'm expecting most of the people watching this video to already know how to solve these things. The most efficient way to do it is to set up an auxiliary equation by using the coefficients of the derivatives to form a quadratic. That quadratic equation can then be solved to get however many roots it has, and then those roots can be plugged into the relevant structure of the complementary function. In the case where there's two real roots, for instance, those roots will go in powers of exponentials with some constants out the front. That's the quickest way to reach the solution, but it doesn't tell us why we're doing any of those steps in the first place. However, some of you might think you already know the answer to that as well, because you're going to turn around to me and tell me that all we've got to do is guess that y equals ae to the lambda x, differentiate it a couple of times so that we can plug it into the differential equation, and then after a bit of factorizing, you can at least see where the auxiliary equation came from. And those of you who are feeling really fancy might even choose to show the independence of the two separate exponential solutions by updating your guess and plugging that into the differential equation instead. However, although this does prove that we've got the correct solution, it doesn't derive it. It doesn't show where the exponentials are even coming from in the first place, let alone even starting to try and unwrap why the repeated roots situation results in an ax plus b out the front of the exponential. And therefore in today's Can We Do That video, we're deriving the solutions to second order differential equations to discover the real reason they look the way they do. And as usual, before we continue on any further, I must warn you, the things we're covering in today's video are just for fun. You don't need to know them for an exam, and in fact I'm actively going to tell you that you should continue solving differential equations the way you already have been doing so far, because that is the quickest way to do it. And some of you might be wondering why this isn't one of my Prove It videos, and that's because the examples we're looking at today will have numbers in them so that we can properly appreciate the magic going on behind the scenes when we solve one of these things manually, rather than covering everything up with algebra as part of generalizing the process. So, let's get started, and interestingly, some of the magic happens almost straight away. Because of course, although this isn't a quadratic, no matter what the auxiliary equation would normally try to tell you, we can use similar strategies that normally work with quadratics. For instance, by looking at the coefficient of y and trying to think of two numbers that would multiply together to make that coefficient, but also at the same time add to make the coefficient of the dy dx term. So in this case, the numbers we want are -2 and -3. What we're going to do is use those numbers to split up the dy over dx term into, in this case, -3 dy over dx and -2 dy over dx. You could have the -3 and the -2 the other way around, it won't matter in the long run. Because what we can then do is we can choose to factorize just the last two terms that we've written, because -2 could be factorized out of both of those things. And if we do that, we'll get this. That's interesting, because it now means we've got a dy over dx minus 3y inside those brackets, but then when we look at the first two terms, we realize that those two terms are also secretly dy over dx minus 3y, but differentiated with respect to x. And so we can rewrite our equation to reflect this fact. That's really nice because it means we can now do a substitution. If we let k equal dy over dx minus 3y, because that is an expression that's appearing in multiple places, the differential equation will then appear much more simply as k differentiated with respect to x minus 2 lots of k equals 0, which could also be rewritten as just dk over dx minus 2k equals 0. And that is really nice, because what we've now got is a first order separation of variables differential equation. We could just move the 2k over to the other side, divide both sides by k, integrate both sides with respect to x, and that will mean we just end up with ln of k is equal to 2x plus an integration constant. You might choose to have a modulus sign around the k at this stage, but either way, it doesn't really matter because we're then going to get rid of the ln immediately by taking e to the power of both sides, and then if you don't like the integration constant being in the power of the e, as usual with separation of variables differential equations, we can do some manipulation to split it up from the power and then rewrite it as a new constant. I've decided to call it d for the moment. The reason this is interesting though is because although we've now found the value of k, that's not the solution to the original differential equation. That was, of course, in terms of y, but don't worry, we've already related k to y when we made the substitution. K was equal to dy over dx minus 3y. So therefore, we've just set up a new differential equation which can also be solved. This one sadly isn't a separation of variables differential equation, but it is one that's still within our skill set to be able to solve because it's a first order exact differential equation. So therefore it's going to be one of those ones that requires an integrating factor, which means we're going to have to integrate minus 3 in the power of an exponential, which will get you e to the minus 3x, and as always you could technically include a plus c in the power there, but in reality it doesn't matter what the value of plus c is, the differential equation will work out the same either way, so pick c is equal to 0 to make your life easier. You've got less stuff to write that way. We can then multiply both sides of the differential equation by the integrating factor and then integrate both sides with respect to x. And as always, with first order exact differential equations, we already know the left hand side is guaranteed to end up just integrating to become y lots of the integrating factor. So that means we only really need to actually put effort into integrating the right hand side. And as capital D is just a constant, when we integrate it we just have to keep the power of the exponential the same and divide by the coefficient of x, so divide by minus 1. And then we need a new integration constant because we've done some more integrating. I've called it plus b for the moment for reasons that you'll see in a bit. And the interesting part is that we're actually almost done by this stage. The only thing we've got left to do is rearrange the equation to make it y equals. So I'm going to multiply both sides by e to the power of 3x. And if I do that, that's where the really cool final step happens, because e to the power of 3x times by e to the minus x is just e to the power of 2x, meaning this is what I'll get. And you'll notice that is where the e to the power of 2x came from and the e to the power of 3x separately. And we could also choose to tidy up the constant that's in front of the e to the 2x by relabeling minus d as the constant a. There you go! And isn't that cool? I absolutely love this process because it means we get to see how the 2x and the 3x form, even though we're expecting them to be there because of our knowledge of auxiliary equations, etc, etc. We now know how they're created, and then we also know about the constants now. They aren't just randomly there, they're actually integration constants, and there's two of them because we started off with the second order derivative and had to integrate twice to reach y. And then we also know where the e came from now because it came from the integrating factor as part of first order exact differential equations, and then also alternatively you could view it as the fact they're appearing because we integrated something that reached a ln on one side of the differential equation. So there you go. This is why I love this stuff. Maths is pretty neat, but is that a proof? Well, no, of course it isn't, because we still have numbers involved. If I want to prove it, I've got to generalize everything with algebra, but that's something we'll leave for a future video in my Prove It series. And in fact, that'll be the next video in that series, so stay tuned for that. However, if you've liked what we've done so far, then please do remember to subscribe to the channel, like the video, and do turn notifications on, because most of the people watching this video aren't actually finding out about my new videos as and when they're coming out. And don't worry, I do only give notifications for the videos in my Prove It series and Can We Do That series, so you won't get notification spam despite the number of videos that I do upload on this channel overall. But we're not done yet today, because I did kind of promise that I'd show you what happens if we've got a differential equation for which the auxiliary equation has repeated roots, because the structure for the solution in that case is a bit different, because there's that ax plus b out the front now, and a lot of you are probably looking at that thinking, why does that look the way it does? Where does that extra x come from? So let's repeat the process we were doing before, but with this new differential equation, so we can see what's going on. So just like as before, we start by looking at the number in front of the y, think of two numbers that multiply together to make that, but also add together to make the number that's in front of dy dx, and of course, in this scenario, it would just be plus 4 and plus 4. We can then factorize the 4 out of the third and fourth terms, and then also realize the first two terms are just a derivative of dy of dx plus 4y. And then, as it happens, as if by magic, you're seeing that dy over dx plus 4y situation happening in more than one place. So to make our life easier, let's do a substitution. Let q equal dy over dx plus 4y, meaning we've just got the differential equation dq over dx plus 4q equals 0. That's just a separation of variables differential equation, so we can move the 4q over to the other side and divide both sides by q to get what you can see right now, and then we can integrate both sides with respect to x. If you do that, you'll get ln of q equals minus 4x plus c. Rearranging to make q the subject of the formula, we can do e to the power of both sides, and then also do some tidying up with the integration constant to write it as an a in front of the e rather than a plus c in the power. Cool, but then we don't want to find what q is, we want to find what y is. So we undo the substitution to replace q with what it was. As before, this is of course just a first order exact differential equation, so we need an integrating factor, which will be e to the power of 4x this time. And this is where the real magic happens for this particular case, because now when we multiply both sides by the integrating factor, the right hand side, the e to the power of 4x and the e to the power of minus 4x will cancel out, meaning we're just left with the constant a. That means that now, if we try to integrate both sides with respect to x, okay, the left-hand side will act exactly the same as normal for these differential equations by just becoming y lots of the integrating factor, but the right-hand side, we're just integrating that constant a. And of course, if you ever integrate a constant, it will just integrate to that constant amount of x. And then because we've integrated, we need another integration constant, so let's call that a plus b. That is why we have an ax plus b in the final solution for repeated root situations, because now when we rearrange to make it y equals, of course we're going to multiply both sides by e to the power of minus 4x, so therefore we end up with y equals ax plus b lots of e to the power of minus 4x. It's so neat, I love it. But in case any of you are wondering what happens with the third case, which is what happens if there's complex roots for your auxiliary equation, well, the reality is it is exactly the same sort of scenario you had with two distinct real roots, because you can still split up the quadratic by thinking of two numbers that multiply to make the number on the end and add to make the number in the middle, and do all the factorizing and then solving the differential equations in the exact same way as we did before. The reality is the only bit that's different with these cases is at the very end, when you convert from something with exponentials to then having some trig functions in there as well. But that bit of the process is something we will save for a future video in the Prove It series. But anyway, that's all I wanted to cover in today's video. Consider checking out some of my other videos. If you'd like to have a go at this process of manually solving a second order differential equation yourself, check out my Can We Do That Some More video on this topic, which is coming out the Monday after this video. And then also, if you enjoyed this video, go ahead, treat yourself and binge watch all the videos in the series so far on my channel. Goodbye!